So to reiterate, we said that the interval of convergence of a series is going to be all of the x values for which the series is equivalent to its function. So the sine of x equals its series for all real numbers, but 1 over 1 minus x only equals its series between -1 and 1. Now, we will sometimes be asked about the radius of convergence. So the radius of convergence is the distance from the center to the endpoint. So basically half of the interval of convergence. So just like the radius of a circle is half of the diameter of a circle, the radius of convergence is half of the length of that interval. So our goal is to know or to be able to find what is the interval of convergence. And the easiest way to do that, because there are many ways to do it, but the easiest way and a way that works every time is the ratio test. So when we're doing an interval of convergence, we will use the ratio test. So in this first example, notice that we have some unknown function, but we're given its series representation. And the first thing that we're asked to do is to find the interval of convergence of that series. So if I'm going to use the ratio test, I know that R, my ratio, is equal to the limit as n approaches infinity of the n plus 1th term divided by the nth term. So I'm going to make my n plus 1 term. Careful putting the parentheses around that, n plus 1. And again, to divide by my nth term, I will multiply by the reciprocal. All right, so there's absolute value around this because we have negative terms in here. But this is going to simplify. Well, let's look at the different parts. So we have an n plus 1 factorial on bottom and an n factorial on top. So in our denominator, we're going to have an n plus 1. Let's see. I also noticed that we had an x to the 2n plus 2, if I distribute that 2 over that on top, and I have an x to the 2n on bottom. And so that's really an x squared on top. So if I have x to the 2n plus 2, I can think of that as x to the 2n times x squared. So the x to the 2n pieces are what cancels out. And then finally, I could really just ignore those negative ones because those are just going to cause like our signs to alternate. But remember, we're taking the absolute value, so we don't even really have to worry about them. All right, so the ratio test will tell us that the series converges when R is less than 1. So for this to converge, I know this is my ratio, and it needs to be less than 1. So notice that this is a limit involving n. So this is a limit as n goes to infinity. And of course, if I was evaluating this limit, I would plug into n, not x. So because of that, we could actually pull the x squared out front. I'm going to keep the absolute value, although I don't really need to because x squared is always non-negative. All right, so our ratio, we just pulled the x squared out front. That's what has to be less than 1. Well, the absolute value of x squared is just x squared. And when we evaluate this limit, when I plug in infinity for n, that limit piece becomes 0. So what I get is that x squared times 0 must be less than 1. And that's just like saying that 0 must be less than 1. And 0 is always less than 1. This is always true for any value of x that we could have plugged in. So because of that, our interval of convergence is from negative infinity to infinity. So in other words, it doesn't matter what value of x I plug into the function in the series will always give me the same value. So in part B, we're asked to approximate f of 0.1 if possible. So I know that's going to work because I'm allowed to plug in any x value. So by figuring out my interval of convergence first, I now know if it's possible to do this approximation with 0.1. But 0.1 is on my interval of convergence because all real numbers are on my interval. All right, so we're going to go ahead and use the series to do this. So f of 0.1, this would be exactly equal to the series if I could use infinitely many terms. And so when I plug in 0.1 for x, I would have 0.1 to the 2n. I have that alternating piece on top. I have n factorial on bottom. So these two things are exactly equal, but we can't use infinitely many terms. We have to use the first three terms. So our approximation comes when we use the first three terms. All right, so if I plug in 0, because this is telling me to start at 0, if I plug in 0 for n, I'm going to get, well, on top, I'm just going to get a positive 1, and I would divide that by 0 factorial. And remember, 0 factorial is 1. I'm just going to kind of keep track of this down here. So that's just 1 over 1. So the number 1. Then I would, my next term, when I plug in n equals 1, my next term is going to be negative because I have negative 1 to the first power. So I'm going to get a minus here. Then I have 0.1 or 1/10 to the 2 times 1. So 1/10 squared divided by 1 factorial. So that's really just 1 over 100. And then when n equals 2, that will give me my third term. So when I plug in a 2, I'm going to get a positive again because I'll have a negative 1 squared. I'll have a 0.1 to the 2 times 2, so to the 4th power over 2 factorial. So let's see, that is, so 1/10 to the 4th power is what, 10,000? So that would be the 2nd power, 3rd power, 4th power. And then I'm dividing that by the number 2. So to get a good approximation here, I should probably get a common denominator. Let's see, so this is really 1 minus 1 over 100 plus 1 over 20,000. When I do that, 1 over 10,000 divided by 2. So my common denominator here should be 20,000. So I have 20,000 minus, let's see, I would have to multiply 100 by 200 to get 20,000. So minus 200 plus 1, we end up getting 19,801 over 20,000. So that is our approximation for f of 1/10. All right, lastly, we are asked what is the maximum possible error in this approximation. So we're trying to figure out how good of an approximation that this is because we don't know the actual value of f of 0.1. So I don't know how close my approximation in part B was. Whenever we're asked about error, we need to look and see what type of series we have. So notice this is an alternating series, and we could see that in the formula, or we could see that in the signs of our terms alternating. So when we're working with an alternating series and I'm finding maximum error, I know that I want to use my first neglected term. So my maximum error will be the magnitude, aka the absolute value, the magnitude of my first neglected term, but that is assuming that our terms are decreasing in magnitude to 0. So that works when our terms are decreasing in magnitude to 0. In other words, when our alternating series converges. So we could tell based on these terms, I had 1, then I had the next magnitude would be 1 over 100. The magnitude of the third term was 1 over 20,000. Those terms are decreasing in magnitude towards 0. So I need to use my fourth term, and that's going to be when n equals 3. So my error will be less than or equal to the magnitude of what I get when I plug a 3 in for n. All right, so that's just going to be, again, I can just get rid of the negative part because I'm finding the magnitude, aka the absolute value here. So I get 0.1 to the 6th power divided by 3 factorial. Let's see, so 1/10 to the 6th power, let's see, that is 1/10 to the 1st power, 2nd power, 3rd, 4th, 5th, 6th power. So that is a 1 with 6 zeros, 1 million. And I'm dividing that by 3 factorial, which is 6. So I get 1 over 6 million. And that is my maximum possible error. So I know that my approximation, my answer, is accurate within like 1 over, or sorry, is accurate to like 1/6 millionth. So I need to know the interval of convergence so that I know that it is okay to use this series to approximate this function. Like that's why we did part A before doing part B at this particular value. And then once I have that approximation, it might make sense to ask how close that approximation is to the actual value.